We know how to add these two vectors together. 4 plus 2, 4 to the right, plus 2 to the right equals 6 to the right. We know how to add these two vectors together. 4 to the right, 2 to the left gives me 2 to the left. No problem, right? What if we have 4 to the right and 2 down? Well, you know what? We learned last week how to deal with those. If we're adding two vectors in 2 dimensions when they're at right angles to each other, we don't have much to do. To find the resultant vector here, which is the hypotenuse of that triangle, we're going to do the Pythagorean theorem. R is going to be equal to the square root of 4 squared plus 2 squared. It's not a huge deal for us. Now, what if we have a situation where we have 4 to the right, 2 down, and then another 2 to the right? Remember the goal of adding two-dimensional vectors together. It is to get a right-angled triangle vector diagram. In this one, we already had a right-angled triangle vector diagram. In this one, we don't even have a triangle, let alone a right-angled triangle. So how do we find the resultant vector that goes from start to finish here? Here's where we got to break it up into our x components and our y components. We've got 4 to the right, and that 4 to the right is 0 up or down. The next one we have is 2 downwards. So that's 0 on the x-axis, and that's -2 on the y-axis. The next one we have 2 on the x-axis and 0 on the y-axis. Add those up, 6 and -2, and now let's redraw it as a right-angled vector, right-angled triangle vector diagram. 6 to the right, 2 down, and we know how to find that. Right, we do the same thing as we did in the last question. R is equal to the square root of 6 squared plus 2 squared. So far, so good? We left you on Friday with this problem, but with a twist to it. One of our vectors on Friday wasn't just straight across on the x-axis or straight up or down on the y-axis. On Friday, we dealt with problems involving what you see up on the board plus a funny angle, an angle of 30 degrees or 50 degrees or whatever the case may be. So let's take a look at one of those now. Let's say we have 4, 2, let's make it another 2, but let's make it up at an angle of 30 degrees right here. When you see this problem, there's a couple things that you think of. Number one, okay, we've got 3 vectors, so we don't have a triangle. We got to break it up in x and y components. But number 2 probably should have been number 1, actually, because it's probably the most important thing you got to think of. It's 5 words. What are they? All of you know what those 5 words are? I don't like funny angles. So let's get rid of it. We got one funny angle here. It's 30 degrees. So let's get rid of it. Let's go off to the side here. Let's label it as 30 degrees. Let's draw a triangle around the 30 degrees such that the angle is inside the triangle. Let's label this as our 2. Let's label this as x, and this is y. And now let's find the value of x and find the value of y. Which side of the triangle is x there? Is that opposite, adjacent, or hypotenuse? You guys comfortable with that? You guys comfortable with opposite, adjacent, and hypotenuse? If it's a right angle triangle, the hypotenuse is the longest side. So this is the hypotenuse. The hypotenuse is touching the angle. So is the adjacent touching the angle. So we know which one's the hypotenuse because it's touching the angle and it's our longest side. This one is the only other one that's touching the angle, so it's got to be our adjacent. If we're looking for adjacent and we have hypotenuse, we're going to use the cosine function. Cosine 30 degrees is equal to adjacent over the hypotenuse. Now the y component is the opposite side because it's not touching the angle. We're going to say sine 30 degrees is equal to opposite over hypotenuse. Let's find the value of x. 2 cosine 30, which works out to be 1.732 meters, I believe, and then the y component works out to be exactly 1. Now, I usually like to draw a little square around that to kind of set it aside. And then I replace this darn 2 meters at 30 degrees because I don't like it. I don't like funny angles, so I get rid of it. I redraw it. I erase that, and then I redraw it as a 1.732 meters to the right and 1 meter up. And now I can deal with this because I just did. That last problem I did on the previous page is exactly like the problem I have to deal with now. Everything's at right angles. Now I just got to get a right angled triangle vector diagram. So let's do that. How? X and Y components. We have 4 and 0 for the first one. The second one is 0 and -2, 2 downwards. What's the third one? What's the X component of the third one, Cody? 1.732. And what's the Y component of the third one, Cody? Nope. Well, okay. I'm looking at the 2 green ones as 1 because I replaced 1 vector with that. Now, if you want to think of that as a 0 and then 0 and 1, that's okay. Or if you want to just put it as 1, which I usually do, what would it be? Yes. Okay, that's okay. If you want to make it 4 vectors, that's fine. You want to keep it as 3 vectors, that's fine too. It doesn't really matter. Let's add these up. 5.732. Add these up. We get -1.0. And then let's redraw it as a right-angled triangle vector diagram. 5.732 to the right and 1 down. And our resultant vector goes from start to finish. You can find that resultant vector by using the Pythagorean theorem. Take a look at that resultant vector. Take a look at this resultant vector. Looks pretty much the same, doesn't it? It should. It's the same vector, except this is just a much easier way, much neater, much tidier way of representing the same vector. A way that we can actually use to find the value as opposed to the first diagram. One of the things that I find when people are solving these problems is that they often try to take shortcuts. They look at this diagram up here and say, oh man, like I got a triangle right here. Right, that's a triangle. Let me analyze that. And then, oh, that's kind of almost a square. No, don't do that. Okay, don't try to take shortcuts with this. Really, don't. Okay, go through the steps, even if it takes you an extra minute or two. Okay, you got a funny angle, get rid of it. Then break it into X and Y components, and don't try to make it shorter. It doesn't take that long to do this. Okay. The end, you go through all these steps, you're going to get the value of R easily. Got it? All right, we have a couple questions for homework. I want to take a look at 2 of those questions now. The first one I want to look at is number 15, and the second one I want to look at as number 16. Number 15 says, we got 3 vectors here. We got a vector downwards that has a value of 5.0 meters. We have a vector to the right that has a length of 8.0 meters, and we have 5.0 meters here at 30 degrees. What do you see first here, guys? What do you see first? Over? I don't like funny angles. So what are we going to do with that? We're going to get rid of it. Take it off to the side here. Draw your 30 degrees. And then let's draw a triangle around the 30 degrees. So the 30 degrees is inside a triangle. This is X. This is Y. This is 5.0. Which side of the triangle is the X component? Shavita? It's adjacent side, right? So we're going to say cosine 30 degrees is equal to adjacent over hypotenuse. And then for the Y component, we're going to say sine 30 degrees is equal to opposite over hypotenuse. All right, let's square this off because it doesn't form part of the main question. Let's get rid of this now because I don't like that. Get a chance to get rid of it, let's get rid of it. We get 2.5 down. We have 4.33 to the left. And then, of course, we have our resultant vector over here. We can do this now, right? We've got 0 and -5. We've got 8 and 0. What's the next one? What's the X component, Matt, of the third one there? Good, excellent. -4.33, and the Y component is? Good, -2.5. Now, if you do it Cody's way, then we would say the X component of the third one is 0, The y component is negative 2.5, but then he'd have a fourth one where the x component would be negative 4.33 and the y component would be 0, right? Doesn't make any difference in the world whether you consider it to be 3 or 4 vectors. What is this? 3.67 and negative 7.5. We'd redraw this. Remember, vector diagrams front to back, front to back. The resultant vector goes down here. You can do that now, right? How many people got that? How many people got that? How many people feel comfortable with that? Good, good. We're going to do one more, and then we'll see if we need to allow you to do one at your desks just for a little bit of practice here, okay? The last one that we had for homework last night was question number 16, which involved 4 vectors this time. One that was to the left, it was 10 meters. One that was down, which was 10 meters. One which was up like this, which was 5 meters. And an angle that's a little bit different because it's labeled from the y-axis instead of the x-axis. And then we had another one that was 20 meters. Down at 30 degrees here. But we sure don't like funny angles this time, right? We got 2 of them. So what do? Take them both off to the side. First one, 5.0 meters right here. This is x, this is y. Which side of the triangle is the x component this time? And on which side of the triangle is the x component, adjacent or opposite? Yes, it's the opposite side. We have the hypotenuse, so we're going to say sine 60 degrees is equal to opposite over hypotenuse. And then we're going to say cosine 60 degrees is equal to adjacent over hypotenuse. Somebody was mentioning to me before class, said, listen, I'm just trying to get this straight. We use cosine for x and sine for y. Is that right? I would say probably 85% of the time or so. Yeah, that's right. Because about 85% of the time, x will be the adjacent side. But when x is the opposite side, we're not using cosine for it, right? We're using sine for it. All right, we get 4.33. We get 2.5. Now, we dealt with one of them. Let's get rid of that one vector just so that we're not trying to do too much at once here. I got something to the right here that is 4.33 and something up here that's 2.5. Okay, let's do the next one. It looks better now. Let's do the next one. Try to finish it off. 30 degrees, 20 meters. All right. 30 degrees, 20 meters. Don't forget to draw your arrows either. Something that drives me crazy when I walk around and I see people with the triangles but no arrows. Draw the arrows. It helps us, especially later on today when you have to find the direction of the resultant vector. X is the adjacent side this time. Adjacent over hypotenuse. And y is the opposite side. Square those off to the side. Now let's replace this 20 meters with 17.32 to the right. And what was it, 10 down? Yeah. Not drawn to scale very well, but that's okay. Resultant will go from start to finish. X's to Y's. John, what's the X component of the first one? X component of the first one? Right here. Almost. Right. What's the Y component of the first one? No. No. 0. Good there? Okay, what's the X component of that one? Yes. What's the y component? Good. There we go. It's all good. What's the x component of the third one? X component of the third one. Let's see. 4.33. What's the y component, Andreas? Yeah. Good. All positive. The fourth one. The x component. McKenna, what's the x component of this one? Good. And what's the y component, Ethan? Good. We add those up. Ooh, I don't know what that is. 21.55, 11.55. Is that right? And this one would be negative 17.5. Find the value of R there? Pythagorean theorem, right? How is that? So good that if I give you a question right now, you're going to be able to nail this thing like nothing. So let's do that. Pretend this is your quiz tomorrow. I want you to find the magnitude of the resultant vector right here, which remember is drawn from start to finish. See what you can do with that for the next 3 minutes at your desks, please. Okay, what's the first thing we see here? Listen, most of us have this tendency to spot things that we don't like before we spot things that we do like. We got a funny angle. We speed that first because we don't like funny angles, so we try to get rid of it. We take it over to the side here. We label our 30-degree angle inside a triangle here. Label this as X, label this as Y, and this, of course, is 100. Which side of the triangle is my 30 degrees? Aiden, which side of the triangle is 30 degrees? Sorry, is the X component, I should say. No. It's the opposite. It's not touching, right? So it's going to be the opposite side. Let's say sine 30 degrees is equal to opposite over 100. X is going to be equal to 86.6. We're going to say cosine 30 degrees is equal to adjacent over hypotenuse. That's opposite of what it usually is, right? Usually it's cos for X, sine for Y. This time it's the other way around. That's okay. That's not 86.6, it's 50. Let's square that off because it's off to the side. And now let's replace that 100 meters at 30 degrees with two vectors. Doesn't matter which one you draw first, by the way. 86.6. Boy, this isn't drawn to scale very well. No, sorry, that's 50, I guess. Still not drawn to scale all that well. I can deal with this now. I know how to do this. I break it up into components. X and Y. I got 100 and I got 0. John, what do I got for the second one? X component is 0. Good. And the Y component is negative 40. And for the third one, finally, what do we have here? Jamie, what do you have for the third one? X component is good, and the Y component is negative 86.6. Excellent. All right, we're going to solve this one completely, guys. 100 plus negative 50 gives me negative 50, negative 126.6. So we're going to draw 50 to the left. We're going to draw 126.6 down, and our resultant vector goes right here. Who has the value of the resultant vector there? Square root of 50 squared plus 126.6 squared. Matt, what is it? Matt? Yep. Yes, that should be positive 50. You're right. Thank you. Mistake there. So that is positive 50. So it's 50 to the right, 126.6 down. The value of R would end up being the same, but you're going to see in a minute the direction wouldn't be the same, and that's important. So we're going to say R is equal to the square root of 50 squared plus 126.6 squared. Matt, did you get an answer for that? I don't think it should be 126 for the 136. 136.1, which we got to round that to 2 digits. We're going to say 1.4 times 10 to the 2 meters. All right, listen very carefully now. Displacement is a vector. When we're adding vectors together, we get a vector. So if we're adding displacements together and we get a total displacement, and displacement is a vector, we needed a direction. For the last couple of days that we've been doing this, we've been giving a magnitude only. And that's okay, but we need to go a little bit further now that we're doing okay with this. What is the direction of it? Okay, if I walk towards Calgary, my displacement is to the north. If I walk towards High River, it's to the south. What's my displacement, including direction, here? If I walk 100 and then negative 50 and negative 40 and negative 86.6. Yeah? You can't say southeast, actually. You can't say southeast because it's in that general vicinity. Southeast would be exactly 45 degrees, and this is not exactly 45 degrees. Right? I wouldn't say south because south is High River. This is taking me towards Blackie or something, right? We've got to find an angle. And the angle is always going to be measured at the start of your vector diagram. There's 3 angles in this triangle, right? Here's 1, here's 2, here's 3. Where do I want to measure it? Position 1, because that's at the start of my diagram. Certainly don't want this one because that's 90 degrees. This one, don't want that one because that's at the end of my vector diagram. We want to know which direction I'm heading, not which direction I came from. What's theta at the beginning of the picture? Now, how do I get that? Well, I have opposite and adjacent. So I'm going to say tan theta is equal to opposite over adjacent. Opposite being 126, adjacent being 50. Now, if you want to actually solve for theta here, pay really close attention to this, okay? Some of you are comfortable with this, some of you are not. Theta would be the inverse tan of opposite over adjacent. So the inverse tan, whatever that means, of 126.6 over 50. Opposite, the one that's not attached to the angle. Adjacent, the one that is attached to the angle but is not the longest one. Now, I'm going to pull this up on my calculator, and I want you guys to follow along with me very closely here. We're going to say, make sure, first of all, your calculator is in degree mode. If it doesn't say degree mode, then you got a problem. You want to put it in degree mode. Then you want to say the inverse tan, which is second function button, tan. Second function, tan. And you got some brackets. 126.6 divided by 50 equals 68.44 degrees. We're going to make this angle 68 degrees. And we're still not quite finished. 68 degrees from what? Like 68 degrees towards the north or towards the south or towards 68 degrees from what? I'm going to say this is 68 degrees south of east. South of east. Now, where does that come from? Ethan told me at the beginning that this is southeast. Well, it's close, but it's not exactly southeast because it's not 45 degrees. So we know our 2 directions here are south and east. But which one comes first? Is it south of east or is it east of south? This is south of east. Look at this. I'm measuring the angle from one axis or another. If I measure it from here, that's measured from the east axis. From here, it's from the north axis. From here, it's from west, and from here, it's from south. This angle is measured from the east. And then from the east, where do I go? South. I go south from east. or we're going to call it south of east. Make sense? If I had an angle labeled like this, that angle would be east of south because it's measured from the south axis, not the east axis. It's measured from the south. So, but I'm going east, so it would be east from the south or east of south. That's a good question. Yeah, no, that's a good question. And the answer is yes, it would change it. But both answers would be correct. Let me show you that, though. It's a real good question. 126.6, 50 meters. Can I draw like that? Sure I can. Because remember, the rule is drawn front to back. Is that drawn front to back? Absolutely. Resultant vector is drawn right here. We solve for the value of r. It's going to work out to be 1.4 times 10 to the 2. But we solve for the value of theta using opposite over adjacent. And theta is going to work out to be 22 degrees. But we're going to say it's 22 degrees east of south. How can those two represent the same thing? How can those two represent the same thing? Well, it's different reference points, right? Okay. High River is 15 kilometers south of Okotoks. High River is 50 kilometers south of Calgary. Are they both right? They both describe where High River is, right? They both correctly describe where High River is, but they're two different numbers. We're using two different frames of reference. We're using Okotoks and we're using High River as our frame of reference. Here we're using the east as our frame of reference. It's south from east. Here we're using south as our frame of reference, east from south. So of course we're going to get two different numbers, but they both represent the same thing. Both of those are correct. That's a really good question. And in the end, I would accept either one of those on a quiz or a test. Yep. Well, if it's multiple choice, you're going to get one of those as an option. Let's say that 68 degrees south of east was the option. You do it this way and you get 22 degrees. Well, don't pick this. Don't pick 22 degrees south of east because you know that's not south of east. You just got to kind of work with it and figure out which one works there. There will be only one correct answer, but unfortunately it'll be my choice of which way it was done as opposed to your choice if it's a multiple choice. The good news is that doesn't happen all that often in multiple choice. Usually those are written questions. All right. Everyone has a map of the first floor of the school in front of them right now. We're going to take a little walk around the school here in the next few minutes to collect some data for a real problem. It's a little field trip. Instead of telling you that a guy walks 10 meters to the east and then 20 meters to the south and then 30 degrees south of east or whatever the case may be, I want you to walk around the school. I want you to plot your path around the school, and then I want you to come back and I want you to add the vectors together. Find the displacement that you experienced as you walked from one place in the school to the other. Now, a couple of things. First of all, I want you to stay on the first floor. Don't go upstairs because then it becomes not a two-dimensional problem, but a three-dimensional problem. We don't know how to deal with those. You're not going to know how to deal with those all through Physics 30. That's a university thing. So don't worry about ever solving one of those problems. Don't create one of those problems today. Stay downstairs. The second thing is this. My suggestion for you would be to turn your paper around a little bit so that it looks more like this. The reason that I would suggest you do that is because it makes the angles a little bit easier to figure out. As far as walking certain distances goes, we're not going to take any tape measures out there. We're going to just paste it off. Okay, you walk 38 steps that way. All right, just write down 38 steps. It's not 38 meters, it's 38 steps. Your unit for displacement is steps today. And how do we find the angle if we make a turn? Okay, let's say we walk up here. Here's my classroom right here. We walk up here. We get to this point, and then we decide, by the way, we should have an arrow there. Then we decide we want to turn down this way. Then we decide we want to turn down this way. And that's where we stop, say. You can make your walk as long as you want, but let's say I just make two turns like that. How do we measure our angles? Well, every time you make a turn, if you have your map oriented like this, I want you to draw a horizontal line every time you make a turn. Now, I don't care where I'm coming from. I care where I'm going to. So when I get to this point, I've got to label an angle for where I'm going. I'm going this way. When I get to this point, I'm going this way. Make sense? What is this angle? You don't have to take a protractor out to measure that. What is it? Nope. You're actually pretty close. Nope, it's 30. This would be 60. How do you know this is 60? Because it's an equilateral triangle. It's the trinity, right? That's why it's shaped as an equilateral triangle, because it's the trinity, 3 equal parts, right? If that's 60 degrees, then that's got to be 30. When I get down here, well, I know that that's 60. So if that's 60, this has got to be 30. Remember, you're measuring the 30 there. I don't care about this. I don't care where I came from. I care where I'm going relative to an axis, usually going to be the x-axis. So draw a horizontal line whenever you change direction, and then measure the angle where you're going from that horizontal line. That angle will always be, in each of these cases, 30 degrees or 60 degrees, depending upon the turn you make. Okay, if you have it drawn reasonably well, you should be able to tell which one's which, 30 degrees or 60 degrees. So plot this when you're out in the hallway, each one of you individually. You can walk with other people, that's fine. Yeah, I don't care about that. But everybody has to have their own diagram here. When you get back to the classroom, having all this data with, 58 steps and an angle of 30 degrees here and another 20 steps and so on, I want you to transcribe this onto a white piece of paper or a lined piece of paper. Just not get rid of this picture of the school in the back, right? We don't want the picture of the school in the back when you go to analyze this because it becomes really, really cluttered. Right, Cody? So transcribe it onto a piece of paper, a blank piece of paper, and then I want you to find your displacement. Add the vectors together. Do what we did back here, except you're doing it with real data instead of cooked up data like I had. Yep. Yeah, that's fine. Yeah, you can do it on the back of that. It's not a handed thing. It's just a little activity for you to do. All right? I'm going to leave you with one more question to do for homework tonight, and it's a doozy. Draw the one that's on the board here, guys. We got 100 meters at 30 degrees, then 50, then 300. Then we've got 50 again, 100 again, and then we got 20 down here. All kinds of vectors. Does this make it harder than any other question we've done? Yes. It's not harder at all. Does it make it more work than any of the questions we've done? Yes, no question about that. We've got 3 funny angles here that we've got to deal with, but we know how to do that, and we deal with them all in the same way. And as far as the other components go, we deal with them in the same ways we've always dealt with them. So I want you to find the magnitude of the resultant vector and the direction of the resultant vector for this one. And then we'll check this one over tomorrow for homework.